Thanks to Adzact for making this video possible. More about them at the end. You don't need me to tell you that sustainability is a big deal. With the natural world taking up an ever-growing part of our collective mindset, corporations are, rightly, under more pressure than ever to live and breathe green practices. But with them all so desperate to be considered in eco-vogue, we quickly run into a dilemma. How can we separate those companies that truly practice the green visions they preach from those that don't? Today, I'd like to talk to you about one rather surprising new gizmo in our green toolbox. In the last few years, artificial intelligence, in the form of machine learning, has well and truly lifted itself out of the realm of science fiction. And when it's not driving cars or summoning demons from beyond the pale, machine learning is rewriting the rulebook on interpreting language with natural language processing. We've all seen plenty of the literary stylings of ChatGPT lately, for example. While far from perfect, this model owes its often shocking aptitude for the written word to some of the technologies we're about to meet. You need three things for machine learning: an algorithm capable of tweaking its own inner workings, a massive amount of training data, and an existing classification of that data. In the case of natural language processing, the data is text content written by humans, and the classification depends on the problem you're hoping to solve. This can range from machine translation, to identifying tweets as positive or negative, to writing questionable Harry Potter novels. The self-tweaking algorithm, meanwhile, comes in many forms, and the present revolution in language processing has been driven by one in particular: the transformer. Transformers are sequence transduction models. This means they take in an input sequence, often a sequence of words, and produce a sequence of any length as output, perhaps of length 1 if you're looking for a single sentiment score. Note that transduction models don't outwardly produce any rules. They don't tell you how or why they know what they know, they just know. The big problem with previous sequence transduction models was a limited memory. Long-range relationships were near impossible to form, traditionally the Achilles heel of AI. For seeing through fuzzy language, this is a problem. Masking beliefs in isolation is easy, but keeping your story straight across an entire corpus is much harder. The Transformer's secret weapon to combat this problem is called attention. When humans process text, we see beyond a sequential list of symbols. We see networks linking words to other words based on known meanings or expected positions. For each word, we've learnt what other related words usually appear nearby, and we can also recognise structures which point to a particular position being the most important for understanding the whole phrase. Attention in machine learning is an attempt to emulate this ability to selectively emphasise and ignore. Based on a learnt understanding of language, for each word, one by one, which other words have the strongest links? And which have the weakest links? Which relationships can we throw away so we can use our limited attention for the links that really matter? At a high level, a transformer first calculates attention within the input only, generating an attention profile for each word. It then conjures some mathematical wizardry to encode these findings into one summarized view of the whole input and its attention relationships, before applying this information to the task at hand, using more attention between the input and output if necessary. If the input is too long to handle all at once, we can split it into manageable blocks and tag the attention output of one block onto the next. This ability to condense and retain the important parts of past information is what gives transformers their sweeping contextual knowledge. But we're getting ahead of ourselves here, because so far our transformer doesn't know anything. Hidden inside this structure are millions of numeric values, known as parameters. Parameters are the weights of routes through the network, the values which determine how information travels through it. Taking various sums and combinations of all of these is what decides where an input word goes, and by fiddling with the parameters, we can change that result. Take comparing word meanings. Computers do this by placing each word at a point in a high-dimensionality vector space, or, as a less abstract analogy, finding the coordinates that place it somewhere on the map of language, clustered with words of similar meaning. To find those coordinates, we start with a random guess. By feeding in the training data, comparing with our expected classification, and applying the full power of linear algebra, we can adjust the coordinates to nudge the word in the correct direction. This is the self-tweaking algorithm at work. make incremental beneficial changes to the parameters billions of times, and eventually, thanks to attention setting us up to optimize for the ideal way of looking at written text, we'll have a model that understands language. Impressive as it may be, training a transformer this way takes a lot of time, a lot of data, and a lot of work. Firing up a bunker full of GPUs every time we want a new model isn't exactly the best way to save the planet, is it? Transformers are at their most powerful when combined with another recent AI game changer: foundation models. Foundation models are the groundwork upon which sit other, more specialized tools. Why bother learning from scratch when others have done the heavy lifting already? Not only does this vastly reduce the carbon impact, but it democratizes machine learning, putting more power in the hands of those without access to acres of server farms. Think of a machine learning algorithm like a schoolchild. Most of us spend the majority of our time in education getting to grips with the basics. Years upon years of schooling just to understand what a noun or a verb is. Armed with a general transferable skill set, we're then ready to specialize. The power to read and write could, with a little more effort, turn you into a journalist or a comedian or a literary critic, or any other expert user of language. Foundation models recognize this separation of educational responsibilities. In the transformer ecosystem, the dominant foundation species is Google's BERT, bidirectional encoder representations from transformers. As we saw, a transformer is an attention-based model which takes in and spits out sequences. BERT begins with this setup and a comprehensive training program, featuring 3.3 billion words worth of Wikipedia and collected novels. From this, it optimizes itself for a few tasks which are meant to give it a general appreciation of language. But what happens if we take such an exemplary student and slice them in half? In some sense, the transformer translates human speak into computer speak and then back into some other, transformed, human speak. All the syntactic and semantic relationships we effortlessly untangle take shape somewhere in between. It's been shown that general language is often understood early on in the network, with only the final few layers acting as the translation back to human land for the specific task. Find the right place to make the cut, and we have a prime candidate for a foundation model, thanks to its encoded representation of language in machine land. In other words, this part of the transformer knows enough to leverage its perspective on language for entirely new tasks with minimal extra effort. In no time at all, we have at our disposal a specialist algorithm. How then can one of these help us classify sustainability sentiment? Our first question is one of data gathering. What data can we provide to reveal the true values of ostensibly green companies? We're talking about language processing here, so we need language distributed by businesses, websites, press releases, etc. What transformers give us here is the ability to view this linguistic output in aggregate. We aim for our model to prise open a company's brain by attending to and comparing content from disparate locations. But for the algorithm to actually know what sustainability-focused messaging sounds like, we can't leave it to grapple with this stuff on its own. If we want to tune the model to our specific dialect, we must assign a sustainability rating to each company in our training dataset. This could be a combination of measures, but in principle, it's simply giving each company a thumbs up or thumbs down, based on its green track record. Who decides who gets which thumb? We'll come back to that. To prepare a pre-trained model such as BERT for fine-tuning, we append one extra block to replace the part of the network we removed. Then, as always, we throw our pile of labelled data at it. Like all neural networks, the model turns the dials in its head in sensible directions until it starts guessing correctly. And since the pre-trained segment is already a highly educated individual, the whole thing needs surprisingly little extra practice to adapt to its new calling. The result? An automated process to identify which companies truly care about the environment based on nothing but their text output. One criticism often levelled against neural networks is that even their creators struggle to see inside their minds. The algorithm has taught itself, leaving its innards a mess of illegible signals that somehow come up with mostly sensible answers. Insert joke about the human brain here. But in a field full of vested interests willing to do anything to keep up appearances, this kind of obfuscation could be an advantage. Sequence transduction models don't spit out patterns or rules to insincerely abide by. A bad actor can do nothing but guess what the model is looking for. Well, not quite. Machine learning evangelists often speak as if it is an unlimited, unquestioned force for good. But algorithms trained on our own text output mirror our own view of the world, and as we've proven many times, not least in our treatment of the planet, our view is clouded. Who chooses what it means to be sustainable? Teaching an algorithm to see through deception is a dangerous game if you can't give an objective answer to that question. A question complicated further when you're relying on a third party to do the bulk of the work. At every stage, we run serious risk of introducing bias. In the worst case, this bias is intentional. But even in the best case, we humans are ignorant, we're resistant to new perspectives, and we portray technologies teetering on the existential precipice as harmless and cute in service of a fun story, when in reality we're dealing with the future of not just our own species, but all of them. We stand at the crossroads of two forces more formidable than any seen before. Climate change and AI are both here, and they will both change the world. But both are products of our own ingenuity, and perhaps, with the right balance of caution and decisiveness, that same ingenuity can thread the needle, finding a way to solve these problems that once seemed impossible. After all, we're getting quite good at that these days. Adzact provide business-to-business marketing solutions making innovative use of language models to build company personas. In particular, they've recently been using the technologies outlined in this video to identify businesses most receptive to sustainability-focused messaging. Visit the link in the description for more details.